Hi guys, in this video we'll begin looking at reactions in this scheme here, Roman numeral 2. These are reactions involving other electrophiles, that is other than H plus or C plus, which we saw up here. And also these reactions do not involve a carbocation intermediate. And that is largely what distinguishes these reactions from those above. The first reaction we'll look at is reaction of an alkene with elemental halogen, with this typically being either chlorine or bromine, and your halogens are diatomic. And this reaction gives a trans dihalide. Now, trans is only going to be applicable in certain cases. But when stereochemistry is applicable, it will be trans. We will see that in the mechanism. Okay, this reaction is shown here in our notes handout. And it's illustrated by this reaction here of this alkene with elemental chlorine, of course again diatomic. And the product is this dihalide. I'm not going to write here, okay, I don't want to clutter it up. We said that here, okay. It's a dihalide. Now in this case, trans is not applicable. At least in the final product. Now this is actually, in terms of predicting the product, and if you do not include any stereochemical discussion, it's actually very easy. You just put a chlorine on each of the original alkene carbons. Carbon here and here, each one gets a chlorine. And in this case, as long as you have the chlorine bonded to that carbon and another chlorine bonded to that carbon, there's no way to be wrong about the product. That is, we don't have any regiochemistry to consider, as we did with a reaction with HCl. Okay, mechanism for this reaction. Diatomic chlorine. It looks nonpolar, and it actually is formally nonpolar, but it's very polarizable. And we can have induced dipole here. And so I'm just going to go ahead and show a induced dipole, and having one chlorine being partial positive and one being partial negative. Now note that your halogens are not ionic. We cannot show Cl plus and Cl minus. All right, can't do that. So we want to use it only covalent. Now this is actually very similar to when we considered HCl or HBr, etc. We have a permanent dipole here, and the H is partial plus and the chlorine is partial minus. And the pi electrons attack the H, and we can move these electrons onto the chlorine. We did that previously over here with HBr. We looked at it as either covalent or ionic. But with the elemental halogens, it can only be covalent. But we're going to do the same type of mechanism here. And I've already got the arrow drawn here for you. Question though, where are we going to leave carbocation? We continue to ask the same questions as before. Do we want to make carbocation on left or right? And the answer is left, because it would be a tertiary carbocation. So electrons pull away from there Okay, pull them away from this left carbon and go make bond to the chlorine. And so the carbon on the right is going to be bonded to the chlorine. And at the same time, we kick these electrons off onto the chlorine to become the fourth lone pair. So this arrow generates chloride, and this arrow generates this carbon-chlorine bond right there, and leaves us a tertiary carbocation. Now, we need to say a couple of things. First off, we could get final product simply by the other chlorine, the chloride that was generated, acting as a nucleophile, and bam, giving a chlorine-carbon bond over here. But that is not the mechanism here. First off, we need to say something about this. This is a carbocation intermediate. But didn't we say that these reactions do not involve a carbocation intermediate? That's right. That's because this carbocation intermediate is not actually formed. I'm kind of lying to you. Now, what actually happens from here is, instead of these electrons attacking and giving you a chlorine-carbon bond, it happens that the electrons from this chlorine actually attack. And why? The reason is, which electrons, which chlorine is closer to the carbocation? The one that's bonded right next door, or the one that's not bonded and it's more likely to sort of wander away, particularly if you have stirring, or in any event, it's more free. The answer is the one that's bonded here, that we just bonded, is closer. It's going to more quickly bond to the carbocation. And that's what takes place, and I'm calling that arrow B, and that leads to a bond between this chlorine and that carbon, and that leads to a three-membered ring. Because the chlorine is bonded to both this carbon, but this arrow makes it bonded to the other carbon as well. And I'm going to call that back bonding. The new group back bonded to make this ring, and that is faster. Okay, that is the intramolecular is faster than the intermolecular. Now, chloride is not a molecule, but inter means two different species. Now, this is not actually formed because these first two steps are concerted. This step and the back bonding step are concerted. What does that mean? That means they happen at the same exact time. All right? That is, these electrons attack that partial positive chlorine, and at the same time, that chlorine, lone pair, is moving back over here to make a bond. Now, some books will show you this, and I'm going to show you a bit more detail than I normally would in lecture, because I have a little bit more time, and I think you will appreciate looking at these details. Some textbooks will show both steps all together. Okay? These electrons attack chlorine, and these electrons back bond. And that electron movement gives bond to chlorine, and 2 lone pairs because there's 2 other lone pairs there, and the chlorine is positive. There you go. And this is the same, okay? That's the same as I showed here. And by the way, this 3-membered ring with a bridged chlorine, okay? It's like if carbon to carbon, you can go across this bridge to get to the other carbon, often called a bridged chlorine compound, is called a chloronium ion, because the chlorine is actually positively charged, which is fairly rare for a halogen. If it was bromine, it would be called a bromonium ion. This is the first and only intermediate in this reaction. If I showed it like this, go from here, here's your first intermediate. Where's the carbocation? There is none. I see none nowhere. So why am I showing it here? I show it here because if I had just showed this, my experience tells me that you will be lost. And some of you may never recover. Because this is just a little bit too much mechanism here early on, a little bit too much for you to handle at this point. So I've always done it by showing the actual carbocation that would form if we did our traditional mechanistic thought that we've been doing with previous reactions. But this is going to help us in other ways. Just make sure that if you do this, you always say NAF. If you don't say NAF, that means you think this is an actual intermediate. It's not. Now, to get to our final product, the chloride, it doesn't do anything here, but here it attacks that carbon and kicks this one back off. Now there's a dipole here. We're not attacking a carbocation. This chlorine is positive. It's very electronegative and it's pulling. It pulls on this carbon because it wants electrons. That chlorine is kind of mad. And we create lots of partial plus here. Now this is shown over here. That chlorine pulling, okay, it's almost like a little pinky bond. It's not a full bond. That chlorine doesn't fully commit. Doesn't fully commit electrons this way. And this is partial positive. Now the question is, would we rather leave partial positive on this carbon over here, or would we rather have the chlorine pull on the other carbon? And the answer is this one here is best, because this carbon can handle more partial positive charge because it is more substituted, it has more rich friends. But here's the answer. This group is going to attack the same place you made your fake carbocation. That right there tells you where it's eventually going to attack. The key point is it doesn't attack a free carbocation. Instead, it attacks a carbon with a leaving group. And we attack and we kick that chlorine off. This arrow gives us the chlorine carbon bond, which is shown here. And when this gets kicked off, this chlorine gets back its third lone pair. And now it's neutral as well. And this is called backside attack. And if you remember, I showed you in the sort of the general handout, the second way here to make a carbon or a nucleophile carbon bond is for the nucleophile to displace, or sometimes I'll say kick off, for the nucleophile to displace a leaving group via backside attack. Okay? And this is usually going to be polarized, all right? And that carbon is usually going to be partial plus. That's why the electrons would be attracted there. So that's what's going on here, backside attack. And that also will bring in some stereochemistry, but I discussed that here. Okay. So this mechanism has one intermediate. I will often show this, but I will always say NAF, because with this we can continue our very similar thought process. I think it's useful to do that. Then the chloride, instead of bonding to a carbocation, it does a backside attack and kicks off the chlorine that had back bonded. That's the mechanism. Now, a good question here that I often get is, why would this chlorine bond back like this to make a three-membered ring, which is strained, and to take on a positive charge? Chlorine is very electronegative. Why would it take on a positive charge when it usually prefers to be minus? Well, the answer is the back bonding gives us an additional bond. We made a bond in doing this, and making a bond is a good thing. And even though the chlorine has a positive charge, it does have an octet, 2, 4, 6, 8. Where over here, a carbocation does not have an octet. So it looks kind of peculiar. It looks like, why would this happen? But we can come up with a couple of arguments for why it would. And indeed, we know it does form. There's actually lots of evidence that it forms. A few of these chloronium or bromonium ions have actually been isolated and studied. So this mechanistic theory has been pretty much proven. Now, let's predict the product. If we don't consider stereochemistry, which we're not doing quite yet, again, this reaction is pretty easy. Elemental halogen, we're going to add a bromine to each carbon. Boom, boom, boom. Bromine here and bromine here. And it's a dihalide. You can go through this, do the same exact mechanism. Really, with reactions, there's often two components, I think. There is the, can you show the product? And sometimes there's a little bit of memorization in there. I mean, that's why we have terms. Okay? I mean, you want to know that reaction of an alkene with halogen gives a transdihalide. You just kind of memorize that. It's also called a 1,2 dihalide. That's because the halides are in a 1,2 relationship. If that's 1, the other one's on the 2 carbon. Okay. There's no stereochemistry to consider in this answer. This reaction can also be done with interhalogens. Interhalogens are where you have two different halogens bonded together, like iodine and chlorine. Now in this reaction here, there's no regioselectivity. Or regioselectivity not possible. Let's say that. Because saying no sounds like there may be times when it would be yes. But it's not possible. What if instead I put this bromine here and that bromine there? Well, that'd be the same compound. So it's not like we chose one regioisomer over another. But down here, regio selectivity is possible. And the question is, will the alkene attack the iodine or the chlorine first? And we have to know a dipole. Chlorine is more electronegative, and so the iodine is partial plus and the chlorine is partial minus. And so the alkene attacks the iodine, kicks off the chlorine. Where are we going to leave cation at, right or left? The answer is left, secondary. So we pull away from the left and we attack the iodine, and these electrons move over to the chlorine as they want to move, and that gives boom, 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 bond to iodine, and leaving this as a carbocation plus Cl minus. But what do we know about this here? This is not actually formed. Why? Or I could ask, what happens next? Will these electrons attack here, or is it more likely for these electrons to attack? Indeed, this happens, and we get boom, boom, boom. Iodine here, but now that is bonded here. Two lone pairs remaining, and that is a positive iodine. We can call that an iodonium ion. Back bonded. Now these two steps happen at the same exact time. As soon as these pi electrons are attacking the iodine is actually back bonding. But I'm not going to show it all together. I'm going to show it separately and just make sure I say NAF. And this is the first intermediate. We can make a general statement. Anytime the new group that's added has a lone pair, it's going to immediately back bond, and it will actually start back bonding right at this point. Okay? And again, the internal or the intramolecular attack is faster than the intermolecular attack. Iodonium. Now the chloride will attack. Will it attack this carbon and kick the iodine off of that carbon, or will it attack this one and kick the iodine off of this one? Well, the answer is right here. It's going to attack that carbon. This carbon can have more partial plus. See, that's a little partial plus. Okay? That positive iodine is going to pull more on this carbon, all right, than it will over here. Because this carbon allows it to be pulled more. Because this carbon has a rich friend that's kind of moving electrons in this way. Okay? Showed that. Again, we really don't have to think about this because the cation right here tells us where we're going to attack. That's where we're going to attack. But instead of attacking a free carbocation, we attack. If I can get in there, okay, I'm attacking that carbon. I got it drawn here. Attack that carbon and kick these electrons back onto the iodine. And that's going to give boom, boom, boom. Now the iodine is still bonded to that carbon. It now has 3 lone pairs. And the chlorine is bonded to this carbon. And of course it has 3 lone pairs because the 4th one is now a bonding pair. And there's your product. And this will be regioselective because we will not get chlorine on the end and iodine here. We would not predict that regioisomer. We would not predict the chlorine to bond to the N region. Instead, we expect the chlorine to be bonded to the second carbon region, or site. Okay? All right. I think I've said enough for now. We'll probably add to this as we go along. Let's move ahead. Again, this is typically either chlorine or bromine, usually not F2. F2 tends to be too reactive to use in the lab, and thus it tends to be fairly rare. If you do thermodynamic calculations, you'll see that it's very exothermic. All right. I mean, this reaction is exothermic, we would expect. We're going from a pi bond to 2 sigma bonds. You can get your calculator out, but it should be exothermic. But if you use F2, it'll be too exothermic and it'll be kind of dangerous, prone to exploding, going boom, too reactive. On the other hand, actually with iodine, it's actually endothermic. Okay? Now that may not be expected upon first glance. But if you take an alkene and try to react it with I2 to theoretically get this dihalide, it usually doesn't work because this product usually converts back and the reaction becomes reversible, and actually this side is more favored with 2 iodines. Now you can often do it with 1 iodine using the interhalogen like ICl, but 2 is not that common. And actually, a little bit of free information here. If you have such compounds, if you were able to make them, this will often convert back to the alkene plus iodine. Now this is just the reverse. But iodine tends to be orange in color. And the reason I point this out is because you may have a colorless product, colorless like water or some like methanol or some common solvent. But as it ages, it starts to turn orange colored, and that's probably because the reaction is reversing and forming elemental iodine. So in the end, this is most commonly seen with chlorine and bromine. Okay, let's take a closer look at the stereochemistry here. How do we know it does not involve a carbocation intermediate? Do we have any actual evidence? Well, we do. And that evidence mainly comes from the stereochemistry that's observed here. If you take cyclohexene and react it with chlorine, you only get the trans isomer. You get the 1,2 dihalide, but the chlorines will be trans. Because it's a ring, we can have fixed geometry here and we can have cis or trans. But you only get trans. You do not get any cis from this reaction. Now, because of that, we say that the reaction is stereoselective. Okay, we get this stereoisomer and not this stereoisomer. But we have to be careful. That's a generic term. Later on, we'll talk about diastereoselective versus enantioselective. Okay? So it is diastereoselective, but it's not enantioselective because we get both enantiomers. All right? Now this is just here for future reference. Now, if a carbocation was formed in this mechanism, we should get both of these. And let me show you why we should get both. Because if this attacked the chlorine and kicked the other one off, first off, where are you going to make carbocation, top or bottom? It doesn't matter. They would be the same. I made it at the top. Now this carbon is now tetrahedral. 4 bonds. I'm going to draw the new chlorine forward. All right? But it can also be back. Because the alkene is planar. Planar like my hand. Or like this. The chlorine can be over here, and the electrons attack the chlorine to the right. Make bond this way. Or the chlorine can be over here and the electrons can move this way and attack the chlorine. The bond can be on the left. Now if I turn my hand like this, electrons can attack up or electrons can attack down. 50-50 chance. And so both of these should be formed. But let's look at this one first. If it was a free carbocation and the chloride attacked there, well, it should also be 50-50 because how do we attack carbocations? Well, right here, 50-50 ratio. Okay? We've already talked about that. And so, you should get 2 outcomes from this structure, from this intermediate. Chlorine forward, chlorine forward. That would be where this attacked up. If this attacked down or from the bottom, we would have chlorine forward and chlorine down. And we would get both cis and trans. We also get cis or trans from this intermediate. The chlorine is down and this one attacked down, we would get cis. If this one's down and this chlorine attacked up, we would get trans. All right? But we know we get trans only. All right? Well, I don't want to mark these out because in this scenario you would get cis. And of course we get trans only because this actually back bonds and that gives alright, the chlorine is still forward, but it back bonded. If it back bonds, that's going to be forward. Or up. If the chlorine is up and it back bonds, the new bond is going to be up. Has to be. Now when the chlorine or the chloride comes in and attacks here and kicks this off, this gives trans. Okay. Trans only. Now hopefully you don't need explanation of why this chlorine is back. If you do, please refer here again to how does a nucleophile kick off a leaving group? That's what's happening here. Nucleophile is kicking off this chlorine from this carbon. Okay? The leaving group is forward. The nucleophile comes in back. This bond is forward. That one comes in back. This is backside. That's why it's back. And now you end up with, when it gets kicked off, this stays forward. Nothing happens here. There. All right. Now we also get this molecule, which is different, the enantiomer. Okay, see where it says plus enantiomer? The enantiomer comes from, okay, we back bond here. These electrons here, and that's going to give that chloronium ion, because if the chlorine's down and it makes a bond to that carbon over there, that other bond has to be down. There's no way for it to be up. Now when the chloride comes in and attacks here and kicks this off, the leaving group is down, so the chloride comes in up, or opposite. You can also call that backside, but again you have to be careful. It's not always back. Backside means it's opposite to the leaving group. The leaving group is down or back, so this chloride comes in up. And so the result would be that chloride is up. You see this is trans, and we do not get that. You only get the two trans. Trans only. Now the one I showed here is actually just like this. This is the enantiomer of that. When I say plus enantiomer, that's the enantiomer. We'll talk about that more. All right. So this is good evidence that the carbocation is not formed, the stereochemical outcome. As I said earlier, some bromonium or chloronium ions have actually been isolated, and here's one here if you want to look that up in the Journal of American Chemical Society, 1994. Usually these are not isolated because they tend to be too reactive and something is going to come in here and open it back up. But once in a while chemists come across one that can be isolated, and this is an example. Okay. Let's look at the next reaction, formation of trans halohydrins. And that reaction is shown here. And we'll see it's going to be very similar, except we're going to include water. And because water is included, we're going to end up with an OH group on one of the carbons. And the OH group and the halogen here are going to be trans to each other. The term halohydrin comes from the fact that there's a halogen in the product, plus also the OH, so it sort of looks like it's been hydrated. Halohydrin. Example here, if we react this alkene with chlorine and water, we get this product as our halohydrin. Now note this reaction is regioselective. That is, the OH is going to be on this carbon, not the other. Okay? our mechanism should show us that. Let's go through the mechanism. Very similar to previous mechanisms. We have chlorine as our initial electrophile. Alkenes don't react with pure water. We can induce a dipole. These electrons can attack that, kick that one off, and that's going to give boom, boom, Cl. Carbocation here, tertiary. This is going to immediately back bond, and that's going to give our chloronium ion, and this is not actually formed. Okay, this is our first intermediate. We also have Cl minus floating around. Cl minus could attack here, but that would give a dihalide. If you include water in this reaction, it will react as the nucleophile instead of the halide. Now usually you're going to have sort of excess water, and that helps it sort of beat out the chloride. Basically, if you do chloronium ion, other things can attack here, okay? Not just this guy. With water present, it attacks, and bam, attack there and kick off the leaving group. That's going to give dump, dump, bump. Leaving group got kicked off. It gets back its third lone pair. Now bonded here is a oxygen. I'm gonna give more room. What if I make it like that? There are my two methyls, and let's make the water here. It doesn't really matter. It's not chiral. The oxygen is bonded. Yes, it's backside. Whenever it matters, we're going to have definitive stereochemistry here. It just doesn't matter here. That's why I'm not being as careful. As long as I get the oxygen bonded to that carbon, one lone pair remaining, that's a positive charge. All right. We don't just magically lose H's. Something's got to take one of these H's. What can take it? Well, this chloride can. Take one of the H's, leave the electrons behind, and that's going to give this product. Two lone pairs. There's our halohydrin. But importantly, if you were asked what else is formed here, what else did we form? HCl. We don't have to guess. We see that in our mechanism. Because when this takes the H, everything goes neutral. So the only difference here is water is included, and what it is, it acts as the nucleophile instead of the other halogen. This gives us an OH in the product. That's called a halohydrin product. Now, why does the water attack here? That is, why does the OH end up bonded here? Well, it's the same as we discussed before. The nucleophile is going to attack the same place you made carbocation. But instead of attacking a free carbocation, we attack a back bonded carbon. And we kick that back bonding group back off when we make the nucleophile to carbon bond. Okay. Now let's look further at stereochemistry. By the way, sometimes this is called addition of HOX because we have the HO and the halogen added. That's sort of generically what's been added in this addition reaction. I want you to do these reactions on your own. We'll look at them in class. Let's see if we want to do this one here. If you take this alkene reacted with bromine and water, okay, first off, we see that we're making a halohydrin. Just, you need to know that. Halogen and water, alkene. But what's going to be the regiochemistry and what's going to be the stereochemistry? We're going to get this product here. I'll work through this, and that's probably where we'll end this video. We've got our electrophilic bromine, partial plus, partial minus. These electrons attack here, these electrons move here. We're going to get new bond to bromine here, and carbocation here. Importantly, this carbon is now tetrahedral, so this is either forward or back. I'm going to draw it forward plus enantiomer. Enantiomer, we'll learn, is where our stereochemistry is reversed. This is not actually formed. This new group with a long pair of back bonds, and that's going to give bromine forward. New bond also forward. Two lone pairs left. Positive charge bromonium ion. This methyl here is back because this carbon is now tetrahedral. Two in the plane, one forward, the other has to be back. Right here it's planar, but now it's tetrahedral. All right, plus enantiomer. Now the water comes in and attacks here, kicks that off, and that's going to give this bromine's forward. Nothing happens to it, it just kicked off from the other carbon. It now has its third lone pair back and neutral. The water came in backside, the bond was up, so the water comes in back, and so this is going to be like this to water. One lone pair remaining, positive charge. Importantly, this methyl group gets pushed forward. Sort of by default. We know the nucleophile is going to come in opposite to the leaving group. They both can't be back. In this process, the existing group gets moved forward. It's like here. This comes in and boom, that group has to be moved over to make room for the incoming group. All right, we'll do more of that later. Now we just lose the H. Something takes it. We made a bromide somewhere, didn't we? Don't we have a bromide? It can take the H, leave electrons behind, and we can get a final product that has the OH back, the methyl forward, and bromine forward. And we see the OH and the bromine are trans, so we can call it a trans halohydrin. And here's your product. All right. Now this is the enantiomer that I told you about. These two are enantiomers. The enantiomers are where everything is switched. Plus enantiomer. Okay, plus enantiomer. The enantiomer of this is this. We could have got this structure if instead of drawing this bromine here forward, if I had drawn it back, both of these back, that would have led us to that structure. Instead, I chose to draw that one forward, and this leads us to this structure. In actuality, you get both of these. Both of these, and you get both of those. A lot of times when we show such products, we show one and we can just say plus enantiomer. Okay, please do these on your own. Chlorine and water, elemental bromine, an interhalogen. And down at the bottom, this is a D. It got cut off there, but that's deuterium. Remember deuterium? An isotope of hydrogen. So this is really just a special HCl. Anytime you see deuterium, the chemistry is going to be just like H. But since it's a D, we often, that's used to kind of bring in stereochemistry. So see what you can do down here. Some to work on. Keep in mind the core fundamental mechanistic knowledge here. We're not just learning to memorize and predict products. We want to work through the mechanism. You know, you can get you a scratch paper and really understand the mechanism. That will allow you to predict any product. And as we move forward, we'll keep reinforcing similar mechanistic principles. Okay? In the next video, we'll look at epoxides and cyclopropanes probably. And then the video for these two is already created from a previous semester. Okay guys, keep at it. Alkene reactions, very important. Very much worth your time working on these. Do remember the alkene puzzle. Okay, some good practice there. For example, alkene with HBr, alkene with bromine. Look at there, bromine and water. Okay guys,